Talk about comparing two categorical variables using the chi-square test. Suppose we want to determine whether males are more likely to vote Republican than females. We've seen this before. We would take a sample of males and females and compare the proportions using a two-sample test. Suppose now we want to determine whether one's gender makes a difference in whether one votes Republican, Democrat, or Independent. This is no longer a two-sample test. This chapter includes two-way tables, the problem of multiple comparisons, expected counts in two-way tables, the chi-square test statistic, cell counts required for the chi-square test, uses of the chi-square tests, and the chi-square distributions. The two-sample Z procedures of Chapter 21 allow us to compare the proportions of successes in two populations or for two treatments. What if we want to compare more than two samples or groups? More generally, what if we want to compare the distributions of a single categorical variable across several populations or treatments? We need a new statistical test. The new test starts by presenting the data in a two-way table. Two-way tables of counts have more general uses than comparing distributions of a single categorical variable. They can be used to describe relationships between any two categorical variables. So here's an example that we'll use to introduce the whole idea of chi-square tests. Market researchers suspect that background music may affect the mood and buying behavior of customers. One study in a supermarket compared three randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the numbers of bottles of French, Italian, and other wine purchased. Here is a table that summarizes that information. So in order to do a comparison, we have a few problems to resolve here. First, we need to calculate the conditional distribution in proportions of the type of wine sold for each treatment. We saw this earlier when we were talking about Simpson's paradox. Make an appropriate graph for comparing the conditional distributions in Part A. And then, are the distributions of wine purchases under the three music treatments similar or different? And we want to give appropriate evidence from parts A and B to support the answer. Now, when no music was playing, the distribution of wine purchases was French, 30 out of 84, Italian, 11 out of 84, other, 43 out of 84, and we see the proportions. These are just obtained right from the table. When French accordion music was playing, the distribution of wine purchases, again, from the table, we get 39 out of 75 for French wine, 1 out of 75 for Italian wine, and 35 out of 75 for other. And so on. With the Italian string music playing, we get the following percentages. So that the type of wine that customers buy seems to differ considerably across the three music treatments. Sales of Italian wine are very low when French music is playing, but are higher when Italian music or no music is playing. French wine appears popular in this market, selling well under all music conditions, but notably better when French music is playing. And for all three music treatments, the percent of other wine purchases was similar. And we can use some bar graphs to represent this information as well. So we're going to talk about the problem of multiple comparisons. Suppose we want to perform a test where the null hypothesis is there is no difference in the distribution of a categorical variable for several populations or treatments. And the alternative would be that there is a difference in the distribution. So we compare the observed counts in a two-way table and the counts we would expect if the null hypothesis were true. The problem of how to do many comparisons at once with an overall measure of confidence in all our conclusions is common in statistics. This is the problem of multiple comparisons. Statistical methods for dealing with multiple comparisons usually have two parts. We first perform an overall test to see if there is good evidence of any differences among the parameters we want to compare. If we find that there is a difference somewhere, we want a detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences are. The overall test in this case uses the chi-square distribution statistic and distribution. Finding the expected counts is not that difficult, and we'll do that here. The null hypothesis in the wine and music experiment is that there's no difference in the distribution of wine purchases in the store when no music, French accordion music, or Italian string music is played. To find the expected counts, we start by assuming that the null hypothesis is true. We can see from the two-way table that 99 out of the total of 243 bottles of wine bought during the study were French wines. So if the specific type of music that's playing has no effect on wine purchases, the proportion of French wine sold under each music condition should be the same. It should be 0.407. So under the condition where there's no music being played, there were 84 bottles of wine sold. Around 40% of those were French. So 84 times 0.407, 34.22. That's what we would expect to be the number of wines sold under that condition. With French music being played, there were 75 bottles of wine sold. 0.407 of those should be French wines. So again, that's about 30.56. And under the condition of Italian music being played, there were 84 bottles of wine sold. And we would expect that around 40% of those would be French. So 0.407 times 84 is 34.22. And then we can do the same for the other wines. The proportion of Italian wines, we have the same arrangement. The proportion of other wines being bought, we have a similar arrangement. So let's consider again the expected count of French wine bought when no music is playing. The values in the calculation are the row total for French wine, the column total for no music, and the table total. We can rewrite the original calculation as this. So the expected count in any cell of a two-way table when the null hypothesis is true is given by the row total times the column total divided by the table total. To see if the data give convincing evidence against the null hypothesis, we compare the observed counts from our sample with the expected counts, assuming the null hypothesis is true. The test statistic that makes the comparison is called the chi-square statistic. And it is a measure of how far the observed counts are from the expected counts. And the formula for the chi-square statistic is the sum of the observed minus expected squared divided by the expected. And that's over all of the possible values on the categorical variable. The chi-square test is an approximate method that becomes more accurate as the counts in the cells of the table get larger. We must therefore check that the counts are large enough to allow us to trust the p-value. Fortunately, the chi-square approximation is accurate for quite modest counts. So the conditions, the requirements here, we can safely use the chi-square test with critical values from the chi-square distribution when no more than 20% of the expected counts are less than 5, and all individual expected counts are one or more. So here is a pair of tables here. We have the observed counts, and then we fill in all the expected counts. So we observed 30 bottles, and the expected count is 34.22. The contribution to the chi-square statistic for this cell is observed minus expected, 30 minus 34.22, squared, divided by 34.22, or about 0.52. And we do that for all of the table entries. In this case, there are 9. And then the chi-square statistic is the sum of all the 9 terms. And in this case, we get a value of 18.28. That's our chi-square statistic. In a sense, it's similar to a z-score or a t-score. It tells us how far away a particular value is from where it should be. Now, the chi-square test is an overall test for detecting relationships between two categorical variables. If the test is significant, we need to look back at the data and learn the nature of the relationship, and we have 3 ways to do that. We can compare the selected percents, so which cells occur in quite different percents of all cells. Compare observed and expected cell counts, which cells have more or less observations than we would expect if the null hypothesis were true. And we can look at the terms of the chi-square statistic. Which cells contribute the most to the value of chi-square? And number 3 is the one that we're going to use at the end of this particular example. So one of the most useful properties is that it tests the null hypothesis that the row and column variables are not related to each other. And that is whenever this hypothesis makes sense. So basically, we're testing the null hypothesis that there is no relationship between two categorical variables. And when we have a two-way table from one of these situations, we have independent simple random samples from 2 or more populations, with each individual classified according to one categorical variable, or a single random sample with individual classified according to both of 2 categorical variables. And software usually finds the p-values for us, and the p-value for a chi-square test comes from comparing the value of the chi-square statistic with critical values for a chi-square distribution. And the chi-square distributions is like the t distributions, it's a family of distributions that in this case, take on only positive values and are skewed to the right. A particular chi-square distribution is specified by giving its degrees of freedom, similar to the t-test. However, that's where the similarities kind of depart. The chi-square test for a two-way table with R number of rows and C number of columns uses critical values from the chi-square distribution, where we take 1 away from the number of rows, 1 away from the number of columns, and multiply those 2. And that's the degrees of freedom. The p-value is the area under the density curve of this chi-square distribution to the right of the value of the statistic. So here is part of Table D from the appendix in the book. And we have, you'll notice, degrees of freedom running down the left side. And then we have the p-scores running across the top. And it's similar to what we did with the t-scores. For example, suppose we have 4 degrees of freedom and our chi-square value is 12.37. To estimate the p-value, we locate row 4 with degrees of freedom 4. And then as close as we can to the chi-square statistic 12.37. Here it falls between these two values. So we say that p is less than 0.02 and greater than 0.01. For example, the null hypothesis is that there's no difference in the distribution of wine purchases at this store when no music, French music, or Italian music is being played. The alternative hypothesis is that there is a difference in the distributions. And our calculated test statistic was chi-square equals 18.28. We want to find a p-value for that. So we have, in this case, 3 rows and 3 columns So we have the degrees of freedom would be 2 times 2. We have 4 degrees of freedom. We locate the row with 4 degrees of freedom. And then the chi-square value is between the values 16.42 and 18.47. So we say this is a small p-value. It's less than 0.0025. This gives us convincing evidence to reject the null hypothesis and conclude that there is a difference in the distributions of wine purchases at this store depending on the type of music that's being played. So because the null hypothesis was rejected, we conclude that there is a difference in the distributions. So to determine which type of music affects which type of wine purchase, we'll take a look at which values contribute the most to the chi-square statistic. So if we just look at a table of the chi-square values, observed minus expected squared over expected, the calculations here show that there are 2 particularly large values. Those actually contribute the most to the chi-square statistic. The others are relatively small. We might consider the 2.3 at some point, but for now we'll just talk about those 2 that are highlighted. So we conclude that Italian wine purchases are strongly affected when French and Italian background music is playing. And if we go back to the original table, we note that the sales of Italian wines are very low, 1 over 75, 1.3%, when French music is playing, but are considerably higher, 22.6%, that's 19 out of 84, when Italian music is playing. We're going to talk about a different test called the chi-square test for goodness of fit. Mars Incorporated makes milk chocolate candies. And here's what the company's Consumer Affairs Department says about the color distribution of M&Ms. On average, the new mix of colors of M&Ms, milk chocolate candies, will contain 13% browns and reds, 14% yellows, 16% greens, 20% orange, and 24% blue. Now here we're going to have a one-way table. And this summarizes the data from a sample bag of M&Ms we got from the store, let's say. In general, one-way tables display the distribution of a categorical variable for the individuals in a sample. So the sample proportion of blue M&Ms in this case is 9 over 60, or 0.15. Now the company claims that 24% of M&M milk chocolates are blue. So we might think that something fishy is going on. We could use a z-test for a proportion to test the hypotheses that the proportion equals 0.24, or the alternative that the proportion does not equal 0.24, where p is the true proportion of blue M&Ms. We could then perform additional significant tests for each of the remaining colors. As we saw before, however, performing a one-sample t-test for each proportion would be, for one thing, inefficient and would lead to the problem of multiple comparisons. More importantly, performing one-sample z-test for each color wouldn't tell us how likely it is to get a random sample of 60 candies with a color distribution that differs as much from the one claimed by the company as this bag does. And that means taking all of the colors into consideration at one time. For that, we need a new kind of significance test called a chi-square test for goodness of fit. So we can write the hypotheses in symbols as follows. And the null hypotheses are that the percentage of blue is 0.24, percentage of orange is 0.2, etc. So these are all equal to what the company claims. And the alternative hypothesis is that at least one of the proportions is incorrect. The idea of the chi-square test for goodness of fit is this. We compare the observed counts from our sample with the counts that we would expect if the null hypothesis is true. The more observed counts differ from the expected counts, the more evidence we have against the null hypothesis. In general, the expected counts can be obtained by multiplying the proportion of the population distribution in each category by the sample size. Well, that's fairly easy in this case. So, assuming the color distribution stated by Mars is true, 24% of all M&M's milk chocolate candies produced are blue. For random samples of 60, the average number of blue M&Ms should be 24% of 60, or 14.4. This is the expected count of blue M&Ms. And using the same method, we can find the expected counts for all the other color categories. So orange, 20% should be orange, so 20% of 60, and so on down the list. Those are our expected values. In table form, we have these distributions of observed and expected. So we can tell almost immediately that the number of blue in expected and observed is quite different. The same would probably go for the yellow. But we want to look at it. So to calculate the chi-square statistic, we use the same formula we did earlier. Chi-squared equals the sum of the observed minus expected squared divided by the expected frequencies. And we have all of these guys. And then add them up. So in this case, the chi-square statistic is 10.18. The process for the chi-square test for goodness of fit. A particular categorical variable has k number of possible outcomes. Each has a probability associated with it, P1, P2, P3, up to the last one. We have n independent observations from this categorical variable. To test the null hypothesis that the probabilities have specified values, that is, that P1 equals some value, P2 equals some value, and on through the last one. First, find the expected count for each category, assuming the null hypothesis is true. Then, calculate the chi-square statistic, the sum of the observed minus the expected squared over expected. And once again, the p-value is the area to the right of the chi-square of the test statistic chi-square under the density curve of the chi-square distribution with k minus 1 degrees of freedom. That is, if we have k possible outcomes, it's 1 minus the number of outcomes. So we computed the chi-square statistic for the sample of 60 M&Ms to be 10.18. Because all of the expected counts are at least 5, the chi-square statistic will follow a chi-square distribution with 5 degrees of freedom. And that will follow it reasonably well when null hypothesis is true. So we're looking for the area to the right of chi-square equals 10.18. Once again, that's the p-value. And we'll use table D again. So here we have the row 5 degrees of freedom, and our test statistic 10.18 falls between these two values, 9.24 and 11.07. So the corresponding areas in the right tail of the chi-square curve with degrees of freedom of 5 are 0.1 and 0.05. So we conclude our p-value is between 0.1 and 0.05. Now in this case, it's greater than the alpha level 0.05. So we fail to reject the null hypothesis. We don't have sufficient evidence to conclude that the company's claimed color distribution is incorrect. We might have just gotten the... So to review this chapter, we constructed and interpreted two-way tables, described the problem of multiple comparisons, calculate expected counts in two-way tables, describe the chi-square test statistic, describe the cell counts required for the chi-square distribution, or the test, describe uses of the chi-square test, describe the chi-square distributions, and finally we performed a chi-square goodness of fit test.